How about that? That's got to be better. So let me repeat it. Welcome to the show. It's Thursday night. This is Alan. Yeah. How about now? You got sound? Yeah, there you go. You got sound. Couple of things. The mic sometimes shuts off on me when I don't expect it. But can you hear me now? Let's see. Can you hear me now? Somebody say. How about now? All I'm getting is a ton of no sounds. You surely have got to be hearing me now. Good now. Something always, too many buttons to push and too few people. So one last time, this is Alan. It's Thursday night. Let's get started. If you didn't enjoy math class or science, tonight is going to be your favorite night ever because we're going to go super theoretical on a few things. One of the pre-statements I'll make, or maybe a caveat that I'll make, is there are probably fewer folks in the world that hate motor tuning than I do. So I don't talk about motors a whole lot because I think they're just a necessity to the whole thing. And there are a ton of people that are way better than me. And we just kind of let other people handle that. If you're into motors and you know better than I do on this, then I have got no authorship or pride in authorship on this. We'll have a discussion about it. But what I want to cover tonight is rollout. And we've had a number of conversations about getting the car super efficient, driving through the corners and all of those things. We've covered chassis. We've covered a lot of pieces here at Sticky Live. But one of the things that we haven't talked about is how do you actually get speed into the car from the motor? And we're going to skip past motor tuning. We're going to skip past all of those kind of pieces. What we're really going to focus on tonight is actually getting the power to the ground, and what some of the theory and calculations are behind that. So let me do this. This is actually what messed up my mic, is I was screwing around with this iPad. So you say to yourself, why are we talking about motors when we're going to talk about rollout? Well, they're actually tied together in a pretty big way. So the thing that you need to know is, first, how does a motor get its rating? Now, what that really means is when you see a motor and it's like, say, 3,300 kV. Now, what this means, a lot of folks, I think, kind of mess this up and they think that that means kilovolts. It actually doesn't. So the crazy science people break this down, and K is equal to constant. And that's kind of, and then voltage, the V is still voltage. So what it means is, if you think about a motor, it actually can also be called a generator. Now, what we do is we feed power in through this way, and then the magnets out here, armature in here, some windings, and this gives us rotational force. If you go the other way, if we were to put a pulley on this and a motor here or a water or something like that, we're going to spin this thing backwards. What that's going to do is actually going to go the other way, and it's going to generate electricity. Now, what they do is they measure that then of how much electrical current is generated per volt of RPMs. So if we have, and that's what the 3,300 means, is, let's do this. Let's give you a new sketch, create, discard, discard. Now, what this means is the 3,300, for some reason, there it is, 3,300 kV. So 3,300 RPMs, 1 volt. So if we have a 10 volt pack, we'll get 33,000 RPMs out of the motor. Oops, that should be an RPM. All right, so let's go through that again. The motor, also known as generator, feed it power. If I feed it 10 volts, it gives me, for this rate of motor, gives me 33,000 RPM. Does that make sense? Let me see if anybody has any questions on that. Nope. So super simple, right? Now, here's where it gets complicated. And this is why I'm beginning with the motor versus the gearing. But we'll get to the gearing because they're both interconnected. There is actually this chart, and we can show it fairly generically. It works for all DC motors. And basically what it says is we have speed across the bottom, and we're going to have torque up here. Now, so as you go up the chart, the torque increases. As you go out the chart, speed increases. And the crazy thing about motors is we can just kind of fake in a line here. Every motor is going to have its own curve, but it's always going to work off of the same principle that there's going to be a point here, which is called the stall. And there's going to be a point here, which is our free rev. Now, that line, so when we set the amp draw on a motor and you've got the pinion off and it's in the car and we're doing the, hey, I want to set it at whatever it is, 3.4 amps. That's what we're getting here is we're actually setting where the free rev is because there's no resistance against the motor. The more amps, the more free rev. And the less amps, the less free because you're moving this back and forth. And we'll get into how that ties in a second. So stall is the exact opposite. And you can do this. We just don't have, you just wouldn't want to grab a hold of one to do it. The stall is actually where the motor will stop turning entirely. It's complete lock rotor. Now, somewhere in the middle here is going to be max power. And you say to yourself, well, that's pretty easy. We get this much speed at this much torque, and that's going to give us the optimal setting. Well, heck, why don't we just set it at that? If it were only that easy. Now, the other end of this, where we have a lot of speed and very little torque, is a low power on a cold motor. So whenever you're like, hey, car just doesn't seem to jump off the corners. It doesn't really want to get going down the straightaway. I got no power. I just can't get heat in the motor. You've heard all those phrases. This is the situation that you've got. You've got a low power cold motor. Now, what that can mean is a couple of things. It could be that the motor cannot generate torque. So in its inability to generate torque, it's just basically getting enough speed and you can get to that position. Or it can mean that you've got gearing way off. It could mean you've got the timing way off. It could mean a number of things. And this is anything between these tips, anything between these two settings, we call bad. Now, the opposite is true, is you're going to have basically a spot in here that is the low power hot motor. And I bet just about every person on here has found where that can exist. The hot motor phenomenon is basically, hey, I smell somebody is burning up out of there, or hey, the motor came in, is 300 normal, or hey, does anybody want some s'mores with this marshmallow that I just roasted? Now, that basically means this, that you've got low speed and high torque, and what's happening is the motor is actually just burning down. Now, anything that happens between these two, we call bad. All the way to the point that the motor stalls out and dies, we call that super bad, because that is like ridiculously horrible, melted the thing down, stinking, burning, smoking. That's what gets into that area, right? So let's look at this a little bit closer in a different way. So if we're saying that we need to find, again, we'll go back to our chart here, speed, torque. If we're saying, hey, I want to go find where that point is. So I certainly don't want to be up here. I don't want to be down here. I want to be into the optimal point on that motor. There's a couple of things that happen. One, we are given the ability to change timing in most motors. Now, what timing does is, and I hate to use kind of a phrase from the pandemic, but it flattens the curve. Now, why do I say that? Here's why. Is flattening the curve means as I turn the timing up, so timing up, it means this point moves out. So what I'm doing is I'm setting now, I've got more, the higher the timing, the more RPMs, we'll call that more RPMs that I'll get out of the motor. In the world of nothing's free, what that means is my line stays here and I end up with less torque. So timing up, more RPMs, less torque. And what I'm actually doing is I'm taking this optimal spot and I'm shifting it around. So now I've actually got, with higher timing, I've got more speed, but I've got a little less torque. And that's going to become a really important thing to mention here in a couple of seconds. So let me switch you back to this. This is what it says. Now, this would be awesome if every track was absolutely the same, because what I could do is I could just say, you know, here's my speed, here's my torque, here's my curve, my timing is whatever, it's going to be 45 degrees. And I know this point, I know this point, I know here. I go out to the track and I've got enough torque to get up off the corner and I've got enough speed down the straightaway going into the corner. That's really what these two things are going to do. This is basically front of the corner, this is out the end. Oops, I should have put end. Now, here's where this gets complicated, is you have got a number of conditions that are playing against you on this all the time. You have ambient temperatures, so as the temperature goes up and down. You've also got the ability for the car to translate speed. Now, what I mean by that is if the car is a little less efficient than it was on the previous run, or it's using more energy in the corners because of the tires, because of humidity, because of all of the things that are going on in the environment, that's going to change what the motor does and how it pulls. Now, here's why this is important. So if I'm going down into the corner, and this is my optimal setting, what it says is I'm going to deliver this much torque and I'm going to deliver this much speed. So if I can get through the corners and this torque is sufficient enough to get me off the corner, drive down the straightaway and get to the end, I'm going to have a fast car. What happens though is I change tires. And this is going to be, so tires, everybody knows this, harder, softer, rolling resistance, oops, rolling so high, low. So just changing the tires, what that can do to my curve then is, again, speed, torque, optimal setting. Here's what I was on, say, a set of greens. When I go to blues, that could mean, or let's use oranges or something like that. It means basically it may require less torque. Now I could potentially get out here and it changes over, revs the motor, or I actually sometimes will end up with less speed, or I can kind of adjust around that. Now, how that happens is this way, is there is no real theoretical line. In fact, if you look at most of the motors you're going to end up with a torque curve that looks kind of like this, and your optimal is actually going to be here. And so as the resistance changes, you're going to hit different points in this line. And here's the other thing that happens. This line moves because of the dynamics of what's going on. So my line may be pulled back in as a torque, and here, hang with me, as the torque is required, I begin to bog the motor. I begin to pull back towards this stall position versus this RPMs. And that's what's going on. So when you say, what's the rollout that, you know, somebody is on, and I hear this all the time. In fact, this is super common. We'll be at Little Indy and somebody will say, oh man, the car is just not as fast. Go throw another tooth on it. What that means is it's one, if you go by the math that's on the iPad here, the track didn't get longer. The motor may have degraded. I'll give you that. The motor may have degraded. Most likely what you've got is an inefficient setup. And now what you're doing is, instead of fixing the problem, you're band-aiding it by over-torquing the motor. And that's what you're basically doing. When you change gear ratio, again, let me clear out of this. It's the same, essentially, as changing the timing. So let me get into this for you really quick. So again, like I said, if you remember, let me give us a line. KV equals constant, with a K, constant voltage. So if I can provide more voltage, again, this is why batteries are super critical. If I can provide more voltage, I'm going to get more RPMs. On the opposite side of this, unfortunately, is if my RPMs, because these two are linked, RPM and voltage are completely linked together. Because I know that 1 volt, in this case, that equals 3,300 RPMs. So if it takes more torque for the RPMs to be generated, it takes more voltage. If I can't generate that out of the battery, that means that the RPMs will drop and the car will be slower. Inefficiency equals a slower car. There's no way around it. Physics are physics. If your car can't drive through the corner, there is no gear ratio that's going to save you. There's no rollout. There's no further to go through the math. So you've got to have the cars right. If you look at the comparison, this is some of the stuff that we talked about a little bit with Tommy, and we've talked about in the culmination of this. Look at that corner and look and see where the inefficiencies are. We can assume for the most part that all the cars are the same speed down the straightaway. Now, we can make some arguments, and there's always going to be that person that's like, oh, well, he's got toe in, or he's got toe out, or he's crab walking, and there's an inefficiency to that setup. Absolutely inefficient can happen down the straightaway. It doesn't matter. It just doesn't. It cannot make up the inefficiencies through the corner of scrub and speed. And these motors have enough base torque, and we have enough base battery that we can overcome the majority of the inefficiencies down the straightaways. I promise you, if you're listening to this, you are not getting beat down the straightaway because of the efficiency of somebody's setup. Chances are their setup's going to be far or worse, better or worse than you through the center of the corner. Now, what that also doesn't excuse, though, is the fact that we're running some math against this motor. And so if we're super efficient, that's where we can begin to fine tune it, or you can begin to get a lot of extra speed. But if you don't have the car right, there's just not saving you. So let's take a couple seconds here and see if we have any comments. Everybody, yeah, all you can talk about is sound. We got that fixed pretty good. Appreciate everybody hanging with me on that. Eventually, we'll get somebody in here to help me with all these buttons. Got to find that sweet spot. Absolutely got to find that sweet spot. So how do we do that and what plays into it? Let's go back to the board. So I cannot read and type and talk and video and everything at the same time. So What is rollout? Let's leave the motor behind for a second. So let's draw ourselves an imaginary wheel. And let's assume there's a line at the top of our wheel. What rollout means is that we're going to have rotation of our little wheel going around. It's on a piece of ground, and it's going to continue to roll, 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 roll. And this line kind of moves around, and eventually the line makes its way all the way back. Now, pretty simplistic idea, but I wanted to kind of explain it for folks that don't do a lot of this. And basically what that is, that's a measurement of the outside diameter of the tire, or the circumference. Now, the math tells us that diameter, it's a lousy D, math in English, times 3.14, which is our friend pi. If you're not familiar with him, it is more than pecan and chocolate. That's going to give us our circumference of the tire, which basically means in inches. If I've got a 2.68 tire, somebody might be faster in this than I am, but times 3.14 means I'm going to have about 8.415 inches of circumference. So that means it's every rotation, the car will move 8.1 or 8.415 inches. Now, why is that important? So let's go back to what is the drivetrain on our car. We have, obviously, we end with a tire. Next to the tire, we have a spur gear, pinion on the motor, and then a motor, right? And then that goes off to a battery and a motor. I should have labeled that. Now, if I've got, let's do an 81, good grief. If I've got an 81 tooth, I've got an 8.415 inch tire. So I've got a 27 tooth spur. I've got my motor, and I won't get into this, but let's say we have 8.4. We're not going to get into this math. Actually, we can. 30. Let's just use a 3,300 kV motor. Now, what that means is my motor, theoretically, again, this is why we build dynos. It theoretically that my 3,400 or 3,300 motor will generate 27,720 RPMs. That's the very best. If that motor is built 100% correctly, that's the very best free rev RPMs that motor will give me. Now, I take these two and I actually divide them, and then we got to put in some parentheses if you're into algebra. 81 divided by 27 is a 3.00 gear ratio. That means every time my motor turns 27,020 divided by 3. So every minute, my spur gear now is rotating 9,240 times because I have reduced this number into this. So my spur gear, this turns, 3 times every time the spur gear turns, which means that I get just a little over 9,000 in rotation. Now, if we go back to that math, that means that we take our rollout and we just take that 9,000, our 8.415 divided by 3, because we have a 2.8 rollout, which means every time my tire or my motor rotates around, it's going to go 27. Oops. Good grief. I should have wrote this down. We're going to travel 27,720 divided by
Okay. We're going to travel 9,000 inches in that. So essentially what it says is I can go through and I can calculate my drivetrain all the way through the theoreticals. And don't worry about too much of the theoreticals, because all we're going to do is completely blow those away. One, because your battery voltage is dropping, your motor is heating, and there's inefficiencies. Every motor is built differently than any other motor. The tires and the rotation and all of those things are constantly changing on us. And so rollout really is only used as a comparison between you and maybe another racer that says, hey, you're super fast at the end of the straightaways. How are you getting there? How do I set this up? And so rollout and gear ratio basically get you in the starting. Now, what that means is that you take a gear ratio, or in this case, a rollout, and you can use that comparative. That's your starting point on the day. Now, what you want to do is really make sure that this math starts working. And so this is what you should be looking for at the end of the day is I have a known starting rollout. Now you can do that by comparing the size of the track or some of the other things that are going on. Yeah, I'll get to that, Jamie, on the transmission. And so basically this is going to be our starting. Now, what we're going to look at is we're going to look in the heat, and we're going to look at lap times. Assuming that you don't have a whole lot of heat, what you're going to do is you'll start going up in either timing in some cases, or you're going to go up in ratio, because you want to get into whatever that optimal temperature you're trying to do. Some motors that's 135, some motors that's 160, but somewhere kind of in that range where you've got that working. And what you want to do is you want to compare your lap times against fast lap times. Now, again, this will not win races if the car isn't there. And if it isn't handling, if it's kicking free, the car has to be working in order for your rollouts, for your motor, for everything to happen. You go up, you hit the wall, you're spinning out, you're loose, you're tight. That's where this thing becomes super important. And so get the car right. Then once the car is fairly right, then begin to work on the motor. It's not, it's kind of, I think folks work on this a little bit backwards. They're like, oh, well, I've got to have more motor. I've got to have this. No, you got to have it the other way. You've got to get the car right, then we can tune in the motor. Because if you're super, super tight, you're going to burn up the motor, or I'm going to gear it lower. And then all of a sudden what's going to happen is you're going to be slow, and you're going to be like, what's going on? Well, the car's tight. Let's free it up some. And you go too free, and then you're going to have other issues. You can't get the car off the corner, and then you got all sorts of other things. So one last piece out of this is what I calculated out was based off of a pinion spur relationship. And you're like, wait, I don't have just that. I've got this little thing on the back of the car, kind of looks like this shape. It's got a gear here. It's got a gear here. It's got a gear here, called a transmission. You need to know that transmission gear ratio. The nice thing is all the manufacturers publish that. So if you get an Associated, you've got a Traxxas, whoever, they're going to give you that gear ratio, and that's going to work into your rollout calculation. So you're actually going to take your, you're just going to enter that in. So it's going to be pinion, spur, then trans ratio. Once you get that, then you take that number and you multiply it. I think it's actually divided. You multiply that by your tire, and that gets your rollout. So let me see how long we've ran. We're right on time. Whoo! Let me take a breather out of that. Anybody have any questions? There's got to be. This is one of those moments where you're like, man, I am glad we got through
through that. But it's actually, it sounds super complicated. It's not. What you want to do is make sure that the motor stays inside of a specific operating range. Now, let me give you one last chart to send you on your way. And here's why that temperature matters. Is discard. Again, back to our ratio. Assuming that we put a more accurate curve in for the motor. This is our motor curve. Everything down here is going to be cold. Everything up here is going to be hot. You can use temperature to actually get you into this optimal band. Now, there is going to be some ambient temperature calculations or how hot the room is, but for the most part, you can do this. So start with, hey, ask around, what are some guys run? If you've never been to the track before, go out with something that you're fairly familiar with the track you ran. Temp it at somewhere around 2 minutes to make sure you're not melting down. If you're cool, then run the rest of the 4, temp it, and then start adjusting in onto that. And if you're down here, just keep marching through, and then eventually you'll get to that optimal setting, and the car should be pretty quick. So again, if the car's working pretty decent, you can use the temperature to guide it in. If the car is pushing, the car is going to be hotter, and if the car is super free, typically it's going to be free revving off, and it may go hotter, but most of the time it'll actually go a little bit cooler. You'll know the difference. So let me go and see what we have got for questions. And one, appreciate a lot of fellows hanging out. This is a little bit heavier topic than we've done the last couple of weeks, but I thought, you know what? We're going back racing, boys. It'll be a fun one to do. So let's see. We've got, yeah, and Mr. Gene, that is, so there's a whole nother thing around that I didn't get into. Diameter of tires, if on a locked ratio, big deal. So we talk a lot about the motor or the tire for spring rate and handling. It's also an incredible tuning tool for your rollout. That's an old 8 scale trick, actually, we used to do too. We had limited choices of the gears that would fit in the car, and we would adjust the essentially the rollout on the diameter of the cars. So great point, absolute great point. Oh no, he's doing the math. Yeah, 88 miles an hour. There you go. Don't forget the transmission. We covered that one. No, Preston, you're fine. You don't need a college thing. Traction roll is your friend. Transmissions are evil. Yeah. Direct drive. Let's see. I'm learning. There's an app for, there are. So a couple of different places you can go. Associated has a really killer app. That's what we use. It's been around forever. It's got about every calculator. It's in the Apple iStore. It's free, I think, still. So that would be the place. Do you have a cheat sheet? Yeah, you have to watch this video over. I was erasing every one of the cheat sheets. Actually, I will be honest, I wrote one up before the show started, but because I was worried I would forget something. I've done that before. Let's see. Will there be a test? Yeah, it comes on race day, brother. Let's see. If you're running a, oh, yes, that is a great example. That's a great one, Reese. If you're running a fan, make sure you turn the fan off trackside so you don't get false readings. If you're running a fan and you are sitting stopped, it's cooling it should be cooling the car off if it's in the right direction. So yeah, absolutely get really consistent with those measurements. Jeremy posted the calculator for gear ratio in that. Need some double purple tire source once again. Tuning tires like that's a killer trick. And Apple Store for my Samsung. phone. I'm sure there's something in the Google store you can do. So a little bit longer topic. I'll give everybody one more round here to any questions on this one. If not, I have got some car prepping to do for the weekend. So we'll pack it up and call it a night. And everybody can go back and make sure that I did my math right on it. Let's see. One last chance, boys. Seriously, who carries double purple tires for pan cars? I have no idea anymore. I would bet, though, that you can get them from RC for less. I would feel really confident that he's probably still got some. How to find a starting rollout? Ask. That's actually the fastest way to do that, Cody. But the other way, in all seriousness, especially with the new track that you guys have got out there, I would go by the length of the track, get a running line, and then compare that to other tracks and just start somewhere around there. And that's probably going to be pretty close to Little Dixie. I would start right on top of that and roll from there, and then go smaller. Smaller tires, depends on what you're trying to do and what your gear ratio is. Smaller tire is not always the better answer on that. All right. That looks like the end for me. 38 minutes long. We try to keep these at 30 minutes. I appreciate everybody joining us. Keep a lookout on Sticky Icky tires. We're going to have a Getting Back to Racing sale. I have a good chance of believing it'll start tomorrow. If you have a chance and you're into retro RC stuff, we have another show on Tuesdays at 8:30 where we do Sticky Icky Classics, where you can watch. We go through basically a car. We're going to do the KO Show versus Tamiya IndyCar battle of 1994. So we're going to talk a little bit about what went on in the hobby back in the, we'll call it the mid-90s on the IndyCar scene. And two Japanese manufacturers got big into it. Should be a fun video. Again, appreciate everybody for watching us tonight, and hopefully you find a place to get racing. Hopefully stay safe, and we will see you later.